All right, let's go. Number 10. The unreasonable effectiveness. In 1960, Eugene Wigner wasn't trying to start a philosophical war. He was a physicist at Princeton, writing what he thought was a modest essay for a math journal, mostly reflecting on why the equations in his own work kept landing on real, measurable things. Standard physics says mathematics is a tool. Humans invented it, like a hammer, and a hammer only does carpentry because we built it to. The setup is simple. Math should only work where we've calibrated it to work. Wigner found the opposite. Complex numbers, invented purely to solve algebra puzzles with no physical meaning, turned out to be the exact language quantum mechanics needed 2 centuries later. Group theory, built by mathematicians solving equations for fun, later predicted particle physics outright. In his 1960 paper in Communications on Pure and Applied Mathematics, Wigner called this a wonderful gift which we neither understand nor deserve. Explanation 1. Coincidence. Math is vast. Some of it was bound to fit. Fails. The fit is too precise, too repeated, across too many unrelated fields. Explanation 2. We only notice the math that works and forget what doesn't. Fails. Wigner specifically cataloged cases where equations predicted results before instruments existed to measure them. Explanation 3. Physical law simply is mathematical, so of course it matches. That's not an explanation. That's the conclusion dressed up as an answer. If Wigner was right, every equation in your phone, in your car's GPS correction for relativity, in the Murray machine that might scan your body one day, was not built by humans. It was found. Who put it there first? Wigner opened the door. What waited on the other side had a heartbeat. Number 9. The Riemann random matrix collision. Hugh Montgomery, a number theorist, was not working on physics at all in 1972. He was trying to understand the spacing between the zeros of the Riemann zeta function, an object from pure number theory tied to how prime numbers are distributed. Standard mathematics predicts these zero spacings should follow patterns unique to number theory, with no reason to resemble anything in physical science. At a chance conversation at Princeton's Institute for Advanced Study, physicist Freeman Dyson looked at Montgomery's formula and recognized it instantly. It matched the statistical spacing of energy levels in heavy atomic nuclei, described by random matrix theory. Montgomery and Dyson's 1972 correspondence, later confirmed numerically by Andrew Odlyzko's large-scale computations in the 1980s at Atten T. Bell Labs, showed the zero spacing statistics of the zeta function match the Gaussian unitary ensemble to remarkable precision. The same statistics that describe the chaotic quantum energy levels of a heavy nucleus like erbium-166. Explanation 1. Pure coincidence between two unrelated fields. Fails. The match holds across millions of computed zeros, not a handful. Explanation 2. Some deeper unifying structure connects primes in quantum chaos, the so-called Hilbert-Playa conjecture, which proposes an undiscovered physical operator whose eigenvalues are the zeta zeros. Nobody has found that operator. It has no proposed physical location, no particle, no field. If primes are secretly governed by the same statistics as the inside of an atomic nucleus, the building blocks of arithmetic and the building blocks of matter may share an ancestor. What operator is Hilbert and Playa's ghost sitting on, and where? The numbers don't just describe reality. Sometimes they seem to already live inside it. Number 8. The fine structure silence. Arnold Sommerfeld introduced the fine structure constant in 1916, simply trying to explain small splittings in the hydrogen spectral lines, a technical correction to Bohr's atomic model. Standard physics predicts that fundamental constants, though measured, should eventually be derivable from a deeper theory, the way pi falls out of geometry. Instead, roughly 1137.035999 has resisted derivation for over a century. No theory produces it. Richard Feynman called it one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man, and in his 1985 book he refused to guess why. The Committee on Data for Science and Technology's most recent recommended value places alpha at 1 divided by 137.035999206, accurate to 1 part in a billion, with the 9th decimal place still unexplained by any first principles calculation. Explanation 1. It's simply a free parameter of our universe, no explanation needed. Fails to satisfy why it sits so close to a clean value without landing on 1. Explanation 2. String theory landscapes predict billions of possible values across a multiverse, and we happen to live in one that permits chemistry. Unfalsifiable, we cannot observe the other universes to check. Explanation 3. Anthropic selection. Life can only ask this question in universes where alpha allows carbon chemistry. That explains observation, not origin. Alter that 9th decimal place, and the chemical bonds holding your own cells together stop working. You exist inside a rounding error nobody can account for. One number holds your body together, and not one physicist can tell you why it's that number and not another. Number 7. The Fibonacci convergence. Eduard Lucas wasn't studying biology in the 1870s. He was investigating the number sequence formalized by Leonardo of Pisa in 1202, purely as a recreational puzzle in integer relationships. Standard biology predicts that plant growth patterns should be shaped by local chemical gradients and evolutionary pressure specific to each species. Unrelated to an abstract number sequence from a different century and a different discipline entirely. Botanists studying phyllotaxis, the arrangement of leaves and seeds, kept finding the same ratios appearing regardless of species. Sunflower seed spirals were counted at 34 and 55 opposing spirals in studies published through the 1990s and confirmed by the American Journal of Botany's Phyllotaxis surveys, consecutive Fibonacci numbers, appearing in roughly 92% of sampled sunflower heads, according to a 2016 crowdsourced count published in tandem with the Museum of Science, Boston, and Trinity College Dublin's Jonathan Swinton. Explanation 1. It's an efficient packing solution. Natural selection converged on it independently. Plausible for plants, but the same ratio, 1,618, also appears in spiral galaxy arm pitch angles measured by astronomers, with no selection pressure of any kind acting on a galaxy. Explanation 2. Coincidental resemblance between unrelated spiral geometries. Fails to explain the statistical precision of the match across scales separated by 20 orders of magnitude. Nobody has unified why a seed head and a galaxy obey the same curve. Your own inner ear, the cochlea, is built on a logarithmic spiral, converging toward that same ratio. The same silent rule seems to reach from a flower to a galaxy without ever announcing what it is. Number 6. Gödel's trapdoor. Kurt Gödel wasn't trying to break physics in 1931. He was a logician answering a narrow question in the foundations of arithmetic, proving that any sufficiently powerful formal system contains true statements it cannot prove from within itself. Standard physics operates on the assumption that a sufficiently complete theory of everything is achievable in principle, even if difficult in practice, a single set of equations from which all physical behavior follows. Stephen Hawking, in a 2002 public lecture titled Gödel and the End of Physics, delivered at the Dirac Centennial Celebration in Cambridge, argued that because physical theories are themselves formal mathematical systems, they may be subject to the same incompleteness Gödel proved for arithmetic, meaning a final, provably complete theory of everything may be logically impossible, not just currently undiscovered. Hawking spent years circling this argument and never resolved it into a working proof either way. Explanation 1. Physics isn't purely formal like arithmetic, so Gödel's proof doesn't transfer. Freeman Dyson argued exactly this in later commentary, but no one has produced a rigorous proof that physical law escapes the theorem's reach. Explanation 2. Even if incompleteness applies, we'll never reach the boundary in practice, so it doesn't matter. That's a shrug, not a resolution. If Hawking's suspicion holds, there may exist true facts about the universe you occupy right now. This instant, that no chain of physics, no matter how advanced, will ever be able to prove. Somewhere in the equations governing your own existence, there may be a truth mathematics is structurally forbidden from reaching. Number 5. The Platonist return. Roger Penrose was not trying to revive an ancient Greek philosophy when he began writing The Emperor's New Mind in 1989. He was a mathematical physicist, investigating the nature of consciousness and computation at Oxford. Standard modern science treats mathematical objects, numbers, triangles, infinite sets as convenient human fictions, invented labels with no independent existence, the mainstream formalist position dominant through most of the 20th century. Penrose broke from that consensus publicly, arguing mathematical structures exist in their own abstract realm, are discovered rather than invented, and that human minds access this realm directly during genuine insight, not merely manipulate symbols. He formalized this into his three worlds framework: physical, mental, and Platonic mathematical, presented across multiple books in a 1996 debate with philosophers published in the Journal of Consciousness Studies. Explanation 1. This is unfalsifiable metaphysics dressed as science. Dismissible on principle. Fails to explain why a working theoretical physicist of Penrose's caliber, a Nobel laureate in 2020, would risk his reputation defending it rather than staying quiet. Explanation 2. It's simply intuition, a feeling of discovery that isn't literally true. Penrose has directly rejected this framing in interviews, insisting the sensation of encountering a pre-existing structure is itself data, not illusion. If he's right, every proof you were ever forced to complete in a school notebook wasn't an exercise. It was a small act of contact with something that was already there before you were born. A Nobel Prize winner spent decades arguing you don't invent numbers. You visit them. Number 4. The 12-decimal ghost. Julian Schwinger, Shinichiro Tomonaga, and Richard Feynman were not trying to build a monument to precision in the late 1940s. They were independently repairing a broken theory, quantum electrodynamics, patching over infinities that made early calculations useless. Standard science predicts theoretical models, however elegant, will always carry measurable error against experiment. No equation matches nature exactly, only approximately. Quantum electrodynamics broke that expectation. Toichiro Kinoshida's calculations of the electron's magnetic moment, refined across decades at Cornell University and published through Physical Review D into the 2000s, matched laboratory measurement to better than 1 part in a trillion, a level of agreement described as the most precisely verified prediction in the history of science. Explanation 1. It's simply a very good theory. Precision is expected of good theories. Fails to explain why no other framework in any field of science, biology, economics, geology, comes remotely close to that level of exactness. Explanation 2. Measurement error hasn't caught up yet. The agreement will eventually break. It hasn't, across 70 years of improving instruments. Feynman himself, in his 1985 book, compared the precision to measuring the distance from New York to Los Angeles, accurate to the width of a human hair. Every screen you have ever looked at, every circuit running this very video, depends on that improbable match holding steady. Nature agreed with an equation to 12 decimal places, and nobody can say why nature bothered to check its work. Number 3. The Mandelbrot intrusion. Benoit Mandelbrot was working at IBM in 1980, not studying nature at all. He was investigating iterations of a simple complex number equation, purely to understand a mathematical curiosity in dynamical systems. Standard science predicts abstract iterative equations run purely on paper or on a computer with no reference to the physical world should produce shapes with no counterpart in nature. Mandelbrot rendered the equation visually and found a boundary of infinite, self-repeating complexity, a shape now bearing his name. Published in his 1982 book, The Fractal Geometry of Nature, through W.H. Freeman. Almost immediately, researchers began finding its signature fractal statistics, not the literal image, but its dimensional scaling behavior, in coastlines measured by Louis Fry Richardson decades earlier. in the branching of blood vessels studied by physiologists at Yale in the 1990s, and in the large-scale clustering of galaxies charted by the Sloan Digital Sky Survey beginning in 2000. Explanation 1. Fractal-like branching is simply an efficient solution to distribution problems. Evolution and physics converge on it separately. Reasonable for blood vessels and river networks, but doesn't explain why a purely abstract equation with no reference to biology or gravity produces the identical mathematical fingerprint before any of those physical systems were measured. Explanation 2. Humans are pattern-seeking and impose fractal description onto irregular shapes that aren't truly self-similar. Fails against the specific numerical scaling exponents that match across scales too precisely to be projection. The blood moving through your own circulatory system right now branches according to a scaling law first uncovered by a man staring at pure abstraction. Mandelbrot went looking inside an equation and found the shape of your bloodstream waiting for him. Number 2. The predicted particle. Murray Gell-Mann was not hunting for a new particle in 1961. He was trying to bring order to a chaotic zoo of subatomic particles being discovered faster than anyone could classify them, applying group theory. An abstract branch of mathematics from the 19th century with no prior connection to particle physics, to sort them into families. Standard science predicts new particles are found first, experimentally, and mathematics is built afterward to describe them. Gell-Mann's eightfold way classification based purely on the symmetry group SU left a gap. The math demanded a particle that hadn't been seen, negatively charged, with a specific predicted mass and a specific predicted decay pattern, before anyone had detected it in a single experiment. In 1964, a team led by Nicholas Samios at Brookhaven National Laboratory's alternating gradient synchrotron found it in bubble chamber photographs, matching Gell-Mann's predicted mass of roughly 1. 672 megaelectron volts almost exactly, and named it the Omega minus, confirmed in Physical Review letters that same year. Explanation 1. Gell-Mann was simply a talented physicist making an educated guess dressed up as mathematics. Fails, the prediction came directly out of the symmetry group's structure, not intuition. The gap in the pattern specified the particle's properties before any guessing occurred. Explanation 2. It's confirmation bias. Physicists went looking specifically for what the math predicted and found something close enough to call a match. Fails against the precision of the mass and decay measurements, which matched the abstract prediction rather than being loosely fitted to it. Every proton inside every atom of your body obeys a symmetry group discovered by mathematicians who were never thinking about protons. An abstract pattern told physicists exactly what to look for in the universe before the universe showed it to them. Number 1. The mathematical universe. Max Tegmark, a cosmologist, was not trying to make a metaphysical claim when he began this work in the early 2000s at MIT. He was trying to explain why physical laws appear consistent, and why mathematics describes reality so seamlessly at all, following directly from Wigner's Old Unease. Standard science treats mathematics as description. Reality exists physically. And equations are our best language for describing it, a map that is not the territory. In his 2008 paper, The Mathematical Universe Hypothesis, published in Foundations of Physics, Tegmark proposed the opposite, that physical reality does not merely resemble a mathematical structure, it is one, with no additional substance beyond the mathematics itself, and that every mathematically consistent structure exists as physically real. Explanation 1. This collapses under Gödel's incompleteness, since no single formal system can be both complete and consistent, undermining the idea of one master structure. Tegmark responded by proposing only computable structures qualify, narrowing the hypothesis, but leaving genuine disagreement in the field over whether the fix succeeds. Explanation 2. The hypothesis is unfalsifiable, since we cannot exit our own mathematical structure to verify it from outside. That objection remains unanswered, and, by the hypothesis's own logic, unanswerable in principle. Explanation 3, it's simply wordplay. Calling reality mathematical adds nothing beyond calling it describable by mathematics. Tegmark has directly disputed this, arguing the distinction is physical, not semantic, in follow-up papers through the 2010s. If he is correct, there is no substance underneath the equations of your body, your memories, this sentence. There is only the equation, running. You were never made of anything. You may simply be the proof of a theorem, running itself to see what it feels like from inside. The universe was never confused about what mathematics is. 10 separate discoveries in 10 separate centuries by people who weren't looking for each other's answers kept arriving at the same uncomfortable seam, abstraction predicting reality before reality shows up to be measured. That isn't the edge of our knowledge. It's the center of our most tested theories. Sitting there in plain sight, unresolved, we built the word invented to protect ourselves from a simpler, colder possibility, that we are not the authors of the pattern. We are something the pattern happened to produce, standing inside it, running the numbers, and calling the discovery our own. If you want to see more videos like this, click the video on screen now.